सुन्नु भएको छ?
हजुर सर, हजुरको आवाज क्लियर छ। हाम्रो छ कि छैन त्यो पनि भेरिफाई गरिदिनु हैन।
हजुर
मेरो सुनिराख्नु भएको छ?
के भन्नुभयो?
ठिकै छ, सुन्या छ भनेको।
ए ल ओके. So as we were discussing that the basic objective for the transmission and distribution system is to transport the generated electrical energy at the generation side to the consumer end. Then why we need this transportation of electrical energy? But just to get that, I have a brief overview or summary of how the electricity is generated and is consumed at the consumer end. So as we know that we have plenty of sources of energy, that is the primary sources of energy. As you know that electrical energy is not the primary source of energy. So we have primary source of energy in conventional sources like fossil fuel, or we have nuclear energy, and in Nepal, as we are very popular in hydro energy. This energy, together with these days, we have the popular sources of renewable energy like wind, or we have solar. There are so many other renewable energy sources also, but these two are becoming very popular like hydrogen energy or tidal or geothermal. But these two are becoming very popular and now becoming a kind of normal energy sources as well. Now, these energy sources ultimately convert. There are some process involved in between to converting into, like from fossil or nuclear, we generate the heat and then the steam is produced, and this steam or the hydro potential itself or wind speed, these are used to rotate the turbine, which convert and the generator converting that kinetic energy to electrical energy. Similarly, we have the solar here written separately because this normally the solar energy is used to generate the DC energy, as you know, and we do not need the turbine. But there is a kind of solar energy as well, which known as solar thermal energy generation, in which the solar energy is used to heat the water or produce the steam, and that steam in turn rotate the turbine and then generate the electricity. But the photovoltaic generation of the solar is very common, so that's why it has been kept apart. Now, when this, by whatever may be the process, ultimately we have the generation of the electrical energy. This energy is ultimately has to be used at the consumer end, basically in these four forms. There are several use of the electricity at the consumer end, but in general we use it either in the form of kinetic energy, like big industries and others. We have so many rotating machines, like even in home we have the fans and others things which need to rotate the some mechanical part, and that we use that energy in the form of motor. Then another very important use of this electricity is the light. As you know that this light is so important that synonymously we use the electricity and light as synonyms, like बत्ती आयो बत्ती गयो भन्नुको मतलब बत्ती बाल्नको लागि लाइट चाहिँ इलेक्ट्रिसिटी चाहिँ हो भनेर सिनोनिमसली पनि हामी युज गर्छौं. The another important use of is the heat energy, or to heat, or like in an air conditioner, or heating a room, or cook for cooking. Like we are very much debating these days in Nepal also whether to cook from the electricity or using by the conventional gases or something like that. So for cooking also, either the induction heater or normal heater, we use the electricity to produce the heat. Similarly, we use the electricity for sometimes for chemical energy. This is a kind of, in fact, the energy storage once we convert it into the chemical energy. But very important is the sources of energy are different than the electrical energy, and also we use this electrical energy for some other form of energy. And to transport that energy from generation side to the consumer, we need the power delivery system. And this power delivery system consisting of both two parts, transmission and distribution. As we proceed, we will distinguish where the transmission and distribution, what's the difference, and how, where we call it as transmission system and where we call it distribution system. The very important part is the electricity neither available naturally or utilized in the same form. That is, do not use, nobody use the electricity just as an electrical energy. We don't need the electrical energy. Just we need the electrical energy to accomplish some other task. Then why we need this intermediate form? Why this question arises that if we do not have this intermediate form, then there would have been no transmission and no need of transporting the electrical energy. The very popular answer I got often from the student is the transportation cost is less. If we, like for example, if we transport the coal, for example, from the coal pit to the where we can use it like coal fire. If we need the heat, we can directly transport the coal and we can produce the heat at the required point, at the consumption point itself. But transporting that coal from coal pit to the consumption side, the cost becomes very high with respect to the if we generate the electricity at the coal pit itself and then transport that energy in the form of electrical energy to the consumer in, and then that energy again used for the heating purpose. So for such type of energy resources it is true. But if we talk about the, like for example, nuclear energy, then we know that the transportation cost for 1 kg of uranium is much lesser than what the transporting the electrical energy what that 1 kg of uranium can generate at the uh, generation side to the consumer side. Then that means this is just a partially it is correct. Then what are the other reasons why we need that this electrical energy as an intermediate form? Then if we go try to explore further, then we get that some of form of energy cannot be transported at all. For example, hydro energy we can generate it only where there is, yes. Do you have any query? Okay. Like hydro energy, एउटा म इक्जाम्पल भन्छु तपाईँहरूलाई एकदम हाम्रो यो लोकस हुन्छ तपाईँहरूलाई थाहा छ तपाईँहरू पनि मेम्बर हुनुहुन्छ होला एकचोटि लोकसमा हामीले चाहिँ यो हाम्रो पावर ल्याबमा भएको हाइड्रो जेनेरेटरबाट हाइड्रो जेनेरेसन गरेर देखाइरहेको थियौँ बत्ती बालेर र त्यहाँ चाहिँ केही भिजिटरहरू आउटसाइडबाट आउनु भएको थियो अनि उहाँहरूले चाहिँ ओहो यो त इलेक्ट्रिसिटी त हाइड्रोबाट त घरमा पनि जेनेरेट गर्न सकिने रहेछ भन्ने उहाँलाई लाग्यो होइन तर यो ट्रु चाहिँ होइन किनभने त्यहाँ त हामीले वाटर पम्प गरेर टर्बाइनलाई रोटेट गरेर जेनेरेट गरिरहेको थियौँ हामी त हाइड्रोको इनर्जी जेनेरेसन त्यहाँ मात्रै गर्न सक्छौँ जहाँ चाहिँ नेचुरल हेड एभाइलेबल छ भने त्यहाँको पोटेन्सियल इनर्जीलाई एक्सप्लोइट गरेर हामीले कन्ज्युमर इन्डसम्म ल्याउनु पर्ने भएकोले पनि हामीलाई इलेक्ट्रिसिटीमा कन्भर्ट गर्नुपर्ने जरुरी हुन्छ त्यसै गरिकन हामीलाई केही फर्म अफ इनर्जी अघि जस्तै मैले इक्जाम्पल दिएँ न्युक्लियर इनर्जीको एउटा कन्फरेन्स भएको थियो अस्ति 1 वर्ष अघि जस्तै हाम्रो आइओईले नै अर्गनाइज गरेको थियो त्यो इन्टरनेसनलै कन्फरेन्स थियो त्यो कन्फरेन्समा चाहिँ म एउटा सेसनको चेयर थिएँ अनि त्यहाँ चाहिँ न्युक्लियर इनर्जीको प्रोज एन्ड कन्सको बारेमा एउटा पेपर थियो र तपाईँहरूलाई एउटा इम्पोर्टेन्ट कुरा थाहा छ कि नै मलाई थाहा छैन तर म इन्फर्मेसन दिउँ कि यो हामीले जुन भन्छौँ नि रिन्युअल इनर्जी why and what's the definition of the renewable energy these days is coming is जसले चाहिँ least greenhouse gas चाहिँ जेनेरेट गर्छ, लाइक CO2 or नाइट्रोजन ग्यास और त्यस्तो ग्यासहरू चाहिँ जसले चाहिँ एकदमै मिनिमम गर्छ। र एउटा भेरी इम्पोर्टेन्ट कुरा के छ भने कि 1 MWh अफ इनर्जी इफ यु जेनेरेट फ्रम द न्युक्लियर इनर्जी सोर्सेस, it's generate even less greenhouse gas than what is generated from the solar 1 MWh or wind. But still, we do not call this nuclear energy as a renewable energy. Then त्यो उसमै म सेयर गरिरहेको थिएँ, अब त्यसलाई जोडौँ। त्यहाँ चाहिँ एक दुईजना पार्टिसिपेन्टले मलाई के सोध्नु भयो भने कि क्यान लाइक सोलर और विन्ड जेनेरेसन हामीले डिस्ट्रिब्युटेड इनर्जीको फर्ममा पनि आजकल धेरै दिज आर रिन्युएबल इनर्जी एन्ड डिस्ट्रिब्युटेड इनर्जी आर अल्सो नोन एज भेरी सिनोनिमसली। यसले के हुन्छ कि डिस्ट्रिब्युटेड जेनेरेसन जहाँ कन्जम्सन छ त्यो नजिकमै राख्ने र त्यो राख्दाखेरि त्यसले पनि ट्रान्समिसन लाइन चाहिँदैन, ट्रान्समिसन लाइनको कस्ट र त्यसमा हुने लसेसहरू बचत हुने भयो। सो क्यान वी युज this nuclear energy as a distributed generation form? I said no. Why not? Because यसले ग्रीन हाउस ग्यास त कम गर्छ तर यसको वेस्ट जुन छ त्यो डिस्पोजल चाहिँ सबभन्दा कस्टली र रिस्की छ। सो बिकज अफ दिस पोटेन्शियल रिस्क इभन द युरेनियम ट्रान्सपोर्टेसन cost is cheaper than the electricity, but we cannot use that nuclear energy where the public density settlement is higher. That's why again we have to generate it far from the consumption point. Then another important reason is very ease and fast control for electricity. Like today, you can imagine that what could have been the size of the computer if we use some mechanical device to rotate the disk and use this. So all these facility nets and other things, whatever have been possible, are due to the electricity. And also it's a faster control, like switch you can make instantly on and off, but mechanical device, as you know, it takes time for making on or off, or time constant is higher. As you might be knowing, the electrical time constant is L by R and mechanical is mass by damping. So this is also using. Now, okay, so that means now we have been convinced that yes, we need to generate the electricity at some site which are may not be exactly in the proximity or exactly at the point where it is used, and that's why we need the electricity transportation, and that the means for that electricity transportation is transmission and distribution, that we call power delivery system in general. Now, another big query is, like suppose we have two generator and two demands on here. So say we have generation 1 and demand 1, and we have generation 2 and the demand 2. What we do not do is, we do not just use this generation 1, whatever energy is generated to the load 1 and generated generation 2 to load 2 isolately. What does it mean? That it does not mean that this demand 1 is for the individual demand. You may say that yes, we do not use it because it is not possible for each and every consumers to have an individual generation. That's why we do not use. I don't mean that this demand 1 is just for individual generator. What I mean specifically is, suppose we have a one power plant like Kaligandeki. Kaligandeki A, as you know, has 144 megawatt of capacity. So what we are calling the demand 1 is, that means there might have been one, that is, if say suppose this area could be served by that, then serve that, use that Marsyangdi, no, sorry, Kaligandeki generated power to that area, and this is Marsyangdi, then use some other area in that vicinity for the Marsyangdi. In that case, also we could have lesser requirement of the transmission line and distribution, but we do not use that. What we do is, we usually make interconnection like this, or like this, or something like this. We interconnect each other, and if we see this, then virtually it looks like that we have a black box where all the generations are connected, and then we have all the demands are connected in the fashion of like this. And for that, we need, like is shown in the another diagram here. So for that also, this interconnection of one source to another, or one source to another demand, or demand to demand connection, then we need the transmission system. And this all whatever is in this box is called grid, power system grid. Then again, the natural question arises: why we need this grid? Why do not we separately do this? Often, whenever I ask to the student this question, then they reply me. The answer is, they say that reliability improves. If we interconnect so many generations and load together, then reliability improves. So let's just see this diagram. Yes, I do agree that if this now what I have just done is, we have made the sum of this both demand here, and these generated two generators are interconnected here at this point. So now, what is the idea of the reliability improvement is, now suppose this generator fails. If these generators go out, then this both of these demand may be made just by from the second generator through this path. Or if this line fails, then PG1 could meet both the demands. But what about if this line fails? If this line fails, then what's the reliability? This reliability may be poor than what was the previously, because now if this section fails, then both the generators have been now the isolated from the demand. So even it is worse than that. In addition to that, we may have this reliability improvement is just not happens if you just interconnect the things. You need some additional cost. For example, I have mentioned you earlier that if this generator fails, then this generator can meet both the demand. What for that purpose, what is requirement is, this generator should must have a sufficient capacity to meet both the demand, this sum of the demand by PG2 itself. For that purpose, we need sufficient reserve margin. Similarly, this transmission link, the link from here to here, should have the capacity to meet, to have the power flow of both the demand one and demand two. So reliability improvement could happen if you interconnect the generators in some sections, but with addition of the cost. If this generator cannot meet both the demand, that this means not just interconnecting each other is not the goal of reliability improvement. So that's why I mentioned that yes, some people say that once we interconnect several generators and demands together, then reliability improves. But this is just a part of the picture. This is not all the causes why for which we interconnect the generators. So for reliability improvement, it is essential that both the generators and corresponding lines, that is this generator and this generator and this line, should be capable to meet the total demand. So reliability is improved by some other means rather than just interconnecting. Interconnecting just itself is not the then what are the causes? One cause is, could be, one reason why we interconnect is just to exploit the demand diversity. What does it mean? Now, suppose that we have as you know that demand throughout the day do not remain fixed; it varies. So now suppose that originally demand one have the daily load curve of characteristics something look like this. It has the peak demand of around 62 or 61 megawatt. So if the demand 1 has been supplied by the generation 1 isolately, then generation 1 should have the capacity of around 61 megawatt. Right? Now, suppose the demand 2 has the characteristic of load curve of look like this. That means it is around 40 megawatt. So again, if the demand 2 is separate, supplied by the generation 2 isolately, then this generation 2 should have a capacity of 40 megawatt in total. So what is the total generation capacity? Again is 61 plus 40, that means around 101 megawatt. Similarly, this line, this common line, we could not have been used in that case. So from here to here, we require 161 megawatt transmission line, and from here to here, we need about 40 megawatt of line capacity as well. But if we connect add these two loads, as you know, then as you can see that the total peak demand peak demand is about just 70 or 71, something like 70 megawatt. So that means in that case, if we do not talk about the reliability, then just if these two generations have the capacity in total PG1 plus PG2, if it would have been about 70 or 75 megawatt, that would have been sufficient to meet both the demand all throughout the time of the day. So that means generation capacity has been reduced, and this is the big advantage. So if once we interconnect the several generations and the demand, there is a reduced generation capacity. What important part I like to mention you is, don't be confused that these two demands is at the same point as it looks from this network. It may happen that demand 1 is PD1 is here, PD1, which is serving this area, and PD2 may be something here, this area. But here, what we are talking here, why we are using that PD1 plus PD2 at this point is, this is the common path from these two source to the load. Now, after that, these two demands diverges. These diverges, but up to this point, we have the common. In this section, we can use the common generation and reduced line. We can use make advantage of reduced line capacity also in case of diverse. And yes, not all the demands are the same. Using the same load pattern, that means always the demands of the individual customers are diverse in nature. Then it's always true that the diversity near the source, that means this part, have higher is observed than in this section, because here we have again even we use this interconnection, but at this section, as you know, that we need to build this as a 61 megawatt line, and this again as 40 megawatt line. However, in this section, even just 70 or 75 megawatt is sufficient. So that means here we can make use of more readily use of diversity. Then another reason could be, these days we are the, as I mentioned you earlier also, that is the renewable energy utilization is becoming very popular. So one of the biggest disadvantage in the renewable energy like wind or solar is, we cannot regulate its generation like in we can do in case of thermal or hydro. In thermal or hydro, what we do is, we generate, though the source is available, but we generate only that amount of electricity which is required by the consumer. But in wind or solar, it is unregulated. What does it mean? That we exploit, whenever wind speed is higher, the generation of the electricity is higher. when the wind speed is lower, the generation is lower. When there is no wind at all, no electricity generation from the wind energy source like solar. What all the solar can generate the electricity during the night? We cannot, but the demand may be at night. And even in sometimes in a day, the generation may be higher than that their local demand. So what we can do is, this is called, these renewable energy are that therefore also called the intermittent source of energy. That means these are there are intermittency. So what could happen that there is always we need some conventional sources in support of that. So now suppose that in the previous example, if this PG1 is a one source of renewable energy like solar or wind, and then the another sources, this maybe this or maybe whatever, this PG2 is either the thermal or peaking run of the river, say PROR, peaking run of the river. So what we can do is, if we interconnect these two together, for whenever this sun or wind is available, make use of this energy, and only the additional energy which is insufficient, we can use this from this generator, or when this energy is not available from this source, then we can use this source of energy. So this may be PROR or maybe thermal energy, but if it is thermal, then there is additional cost is involved. In such cases, we may need it to keep it warm again, even it is not generating the electricity, because otherwise it takes long time to start up. So, assuming PG1 is solar or wind and PG2 as PRO hydro, we can, PG1 is utilized when this source, the renewable RE is available, else we use the PG2. But this possibility has become true only if we interconnect these sources. Then there are now these days, as you know, that the still, though we are using the conventional system of power generation, transmission, and distribution in our country, but most of the countries has already gone in deregulated market, and there is strong advocacy in even in Nepal that we should go for the deregulated energy market. In deregulated energy market, what happens that there are several generating companies, and there are several the distribution or the wholesale purchaser companies which distribute the electricity to the consumers. So what they do is, at any instant of time, say 12 o'clock today or tomorrow, all the generating companies bid for that, if you purchase the electricity from us at this time of the day for that day, we can offer you the electricity at this rate. So always there is the purchaser has the opportunity to purchase the electricity from the least cost offer, which is least cost. So now suppose there is one scenario, one particular instant of time. So there is a demand of 1500 megawatt at this point, end point, and there are four, five, six number of generators which are interconnected to each other are available. These four, as you know, is the wind energy source, so its running cost is almost nil. So they are ready to offer the energy to this demand of by just $20 per megawatt hour at that instant of time. Whereas this may be the thermal power plant, and it's offering at the rate of $50 per megawatt hour. But this may be, say, diesel plant or something like that. So they say that no, if you purchase the electricity from us, we can offer you only at the rate of $100 per megawatt hour. So $100 means it's about 10,000 Nepalese rupees. So that means 10 rupees per unit is of something practical range. So otherwise, if there would have been no interconnection, it has the choice, this demand, that it should take from here. But now, what they can do is they can first, this is the list cost. So 50, 50, 50, 200. So they will take 200 megawatt from here. Then next higher cost is this. So they will take the 1000 megawatt from here. So in this line, there may be 1200 megawatt power flow, and only remaining 300 megawatt could have been flow from here. But this is possible only if this is interconnected, not only interconnection, this line should have the sufficient capacity of to allow the power of 1200. Now, if this line would have been just 800 megawatt capacity power flow, then there would have been no choice other than purchasing the 700 megawatt from this. So we can see that this could have been this is the scenario provided the transmission line constraint is not there. And just what I want to convey you is that is if we interconnect the several generators together, then we have a least cost operational flexibility, and this is the reason how the deregulated market is coming into the play. That is competition. Without interconnection, there would have been no possibility of competition. Okay, so these are the operational or some other form of advantage. But I have to mention you the two major technical reasons that why the generators are connected together. One important, very, very important is the loading effect. What is the loading effect? As you all know, that the generator equivalent circuit you might have studied. So say this we have a generator, the generator equivalent circuit, something look like this. So this is called synchronous generator, and this is called the back EMF, and load is connected if at this terminal, say load, then we call this as terminal voltage, terminal voltage. So obviously, very simply, as you know that this Vt, the terminal voltage, is expressed as this E minus I into Zs. This Zs, as you have studied in the electrical machine course, was known as synchronous impedance, which includes both the armature reaction impedance as well as the leakage impedance. So this Zs. Now, as this load increases, what does it mean? Increasing the load means the power current flow through this is increased. And once this I increases, then this terminal voltage goes on decreasing, isn't it? Now, what could happen if we have another generator also there? So, we have another generators also, like this has also similarly have a synchronous impedance of Zs, and or maybe this is Zs1 and this is Zs2. Of course, E1 and E2 cannot be interconnected together, so this is E, both have voltage of the same. This is the mandatory connection for the so now suppose this is connected like this. Once we say that several generators are interconnecting, that means virtually we are saying that these generators are connected in parallel. So now, if we write again the same equation for the terminal voltage, it is E minus, again load current I into Z equivalent, where this Z equivalent is the parallel of Zs1 of Zs2. And as you know that always the equivalent impedance of the two parallel impedance connection is lesser than individual. Or say for example, if Zs1 is equal to Zs2, then Z equivalent is ZS by 2. So in that case, this would have been ZS by 2. Once this impedance is reduced, then there will be less drop in terminal voltage. But you may ask one question: are you making me the fool? Because once we interconnect these two generators, the current also increases, isn't it? So you may ask this question that if Z equivalent is half, then this current may be twice of that. That is, again, this current will change because this current also flowing. The load will increase once we interconnect the two generators in parallel. Then what's the meaning of that? Yes, you are right. If we just interconnect two generators, just imagine if the several such generators are interconnected in parallel, like number of ideally saying infinite number of such generators are interconnected in parallel, then what happens? Then the Z equivalent is Zs upon infinity. So that means Z equivalent tends to 0. And once it tends to 0, anything multiplying by 0 is 0. So what happens that just I can give you the very practical example for this purpose. Like in your home, you get this, you are getting the supply. Say, imagine that you are getting supply from the grid. You one by one, you switch on all the electrical appliances you have in your home, all the bulbs, all the freezes, TV, iron, and then fans, AC, whatever you have in your home, make it all the on. What you will feel? You don't feel there will be much change in the voltage. But suppose now you are not getting that electricity supply from the grid, but you have a portable generator in your own to your house, and you are doing repeating the same thing. You are one by one, you are going adding all the bulbs, all the ACs, all the trees, and everything, whatever electrical appliances you have in your home. Then what happens? Now in this second case situation, the voltage in your home becomes very less. Why not in previous case? Because that so number of many number of generators in previous case are connected in. So individual or four or five or some few number of consumers, if even they operate in the peak, it not make this very much difference. Yes, even in that case, there is one chance when the voltage could be lower, and that is not during some individual consumers peak time, but we call that as system peak. So when there is a system peak, then only there is some drop in, or the voltage is shown little bit below. Otherwise, this voltage is more or less remaining intact at the same value, even without much variation. Even the load, as you know, that varies continuously. So if the infinite number of such generators are connected in parallel, then their equivalent impedance is ideally 0, and that's why we also call it as infinite bus. This bus is defined as infinite bus, assuming there is no fluctuation in voltage at all. So just that I have shown in the here. Uh, Parallel connection reduces the overall impedance. Loading effect is minimum, less voltage drop. So ideally, if infinite number of such generators are connected in parallel, equivalent impedance is 0 and no loading effect. Very important to remember. You might have heard the name infinite bus, but why it is called infinite bus is that means we are assuming ideally that for practical infinite bus there is some voltage fluctuation, and usually during the peak time. But ideally, infinite bus have no fluctuation of the voltage at all. Another technical advantage is, you know that we have, say, we have a generator, this generator, and then we have a demand. Okay, so say this is the electrical energy demand at this generator, and this generator is getting the input of mechanical power of Pm. Then you know that you have already in power system stability derived this equation known as swing equation. This swing equation is not valid, not only valid for your transient stability, whatever you have studied in there, but it is valid throughout. Even this in transient stability, what? Hello? In transient stability, what you have assumed that the variation in this PE is very, very high, and that's why you assume that Pm remains the same and you solve this equation. But this equation in general is valid even during the transient condition, even during the gradual change in the electrical energy. If there is a gradual change in electrical energy, the system may not be unstable, but may the frequency will change. So how much the frequency will change is decided by this. This is the acceleration of the rotor acceleration. This d squared delta by dt square is the signifying the acceleration of the rotor. So if the rotor accelerated more, the frequency change will be more. If it will be less, then, and how it is controlled is either the difference of these two or by this. So if this deviation is small, then this acceleration will be less. But suppose that your deviation is constant and you desire that acceleration should be as low as possible, that is, the frequency deviation is minimum, then only option is this h should be high. And what is this h? This h, I hope that you remember, is called inertia constant. So it's coming from the generator inertia. So in this equation, if this 2h by omega s is just the synchronous speed, is not varying much, is higher, even for same Pm minus Pu, the acceleration is lower. Now, what could happen if we have multiple number of generators? Say we are connected together. So we have one generator, we have another generator. All these generators are now connecting at this common system. Say PM1 is here, PM2 is here, and PM3 is here. And now you have previously the individual demand P1, P2, P. So now you have total P, which is the sum of PE1 plus PE2 plus PE3. So if you write this swing equation for individual generators, then you could have 2h1 upon omega g square. And now we are saying that all, whether whatever with the frequency of the system will the same as it is connecting together. So acceleration will be the same, Pm1 minus Pe1 2h2 omega g square del by dt square Pm2 minus P2. Just take example for two cases, two generator cases. Now, if you add this, this is Pm1 plus Pm2 minus Pe1 plus Pe2, and here you get 2h1 plus h2 by omega d square L by dt square. Now, this is, if in equivalent case, you can call it as Pm minus Pe. What you have seen is now the equivalent inertia has been is increasing if we interconnect many generators together and it swings together. Then what would have been the case if infinite number of such generators are connected parallelly? Then this as tends to infinite in case of infinite number of generators interconnecting together. As you know that ideally we call it infinity, whenever we call infinity in electrical engineering, but practical meaning that there are many. So beyond a certain value of, as we call it, is infinity, or beyond a certain number we call it infinite number. So this as tends to infinity, and then what happens that even there is a fluctuation in this E, there will be no fluctuation in mm, frequency, or there is a less chance of system going in out of synchronism in case of transient disturbances. So in case of multiple generators, as I have told you just right now, this is the scenario. So for several number of generators, inertia tends to infinity and ideally no frequency deviation. So this is the these are the reasons, in fact, really speaking, that why we interconnect all these generators. So there is a definition, ideal definition for this is very important definition. You must remember what is the meaning of infinite bus. Whenever you go for the interview after the passing of the electrical engineering, and so you may be asked, what do you mean by infinite bus? So what is the infinite meaning of the infinite bus is ideally there is no voltage and frequency fluctuation. That means there is no fluctuation in voltage and no fluctuation in frequency. And how it has been become possible? It has been become possible only if we interconnect several number of generators in parallel or together from a single source, and we cannot expect the infinite bus because that have been the loading effect, and ultimately there is a fluctuation in voltage and frequency. Okay, so with this, now you have a little bit idea of that there is a generation at some point, then we have the consumers, and these generators are interconnecting with the among themselves and with the different loads, and for that we need a power delivery system to interconnect all these sources and the consumptions, and we call the power delivery system. What is the power delivery system? What uh, is the main objective of the power delivery system? So the primary mission is to deliver from the power from the source, that is generation, to electrical consumers at the place of consumption. Very important, at their place of consumption and ready to use form. What does it mean by place of consumption? I will go for one by one these two separately. What's the place of consumption? Now, by now, you might have been understood that how we can imagine the electrical power system is looks like, if you imagine, just think as a tree. I hope that all of you are familiar with the tree. In tree, what happens that there are several roots of the tree. There are several roots of the tree, and these roots support a very bulky part, and then it has the branches. It has the branches and sub branches, and then ultimately there is leaves, right? You have leaves. So just think that leaves, tree leaves are the consumers. These roots, these roots are are the source like of energy. That means all these are the generators, all these are generators, and these are the consumers. Consumer 1, consumer 2. So how it has to be distributed is, first initially in the bulk amount, then diverges. Some say initially it takes P, then now P1 is going here, P2 is going here. Even from P1, we have P11 is going here, P12 is going here. So initially it is taking the power in bulk amount. So many And this must be this the power system as a whole, and this whole is a power delivery system. This in all is a power delivery system, so it must be dispersed throughout the service territory in a rough proportion to customer location. That means where the customers are larger, it should go there in more amount. Near the source in bulk goes on reducing near the consumptions. Now, again, should have the sufficient capacity. That means this section, I repeat again now. I have just what happens that what does it mean that now you have look like the power delivery system as you have seen is look like here, but this line should have a capacity to carry out all these power flow. But this line only need to have a capacity to meet this. That means even all these are interconnecting to each other, the different lines should have different capacity and different distance to travel. And it must carry out those without making. What does it mean by peak demand and why I have mentioned it separately, peak demand and energy demand? I will tell you later also, but at this instant of time you just understand that whenever we say peak demand or peak generation in megawatt in power system, we mean that this is the indicative. This when we say the in terms of power in megawatt, it is the indicative of investment. And whenever we say in terms of energy, then it is the meaning of return. Like, for example, we want to have a generation, have a 100 megawatt capacity. That means, what does it mean? You need to invest for 100 megawatt. But what's the return you are getting? Once you are installing a 100 megawatt generator, is it guaranteed that all the 100 megawatt generators giving the same return? No, return depends upon the how much energy that generator has generated or sold to the consumers. So in power system, the peak demand and energy demand has two different meanings, and this is valid also for the transmission line. So say for example, if you have to build a transmission line for 200 megawatt, that means you have to invest for the 200 megawatt, whether that line carry the power throughout the day, throughout the year, or just in few months of the year, or just 2 hours each day. Irrespective of that, you need to invest for 200 megawatt that transmission line. But the return will be higher if more and more energy is delivered to from that line. Another, this is of course a requirement for all the system that it should be reliable, and it is whenever the consumer requires the power, it should go to the in a reliable manner. Okay, ready to use form. What does it mean by ready to use form? Is that consumers should get the electricity at a voltage or something relate for based on their equipment rating. For example, if 11 kV will be sent to your home, can you use it? No, because all of our home appliances devices are rated for 230 volt single phase or 400 volt three phase. So we must get the power in electrical energy at 230 volt in our home. Some industry may have some bigger motors and they require the electrical energy at some 11 kV or something that. Then there the electricity must go for at 11 kV or 33 kV or 3.3 kV, whatever is required. So it must be in the requirement. Or somewhere in some countries, the utilization voltage is 100 volt only. Then there is no use of sending the electricity to that consumers at 230 volt. They cannot use that their appliances. For that, the voltage must be 100 volt. So it is in ready to use form. So that means the customers should not is be responsible to convert it into their suitable form or ready to. And as I mentioned, that it's very important that the voltage must be stable. What does it mean? That, for example, our fan, as you know, is the induction motor. An induction motor, how it rotates, it produces the torque, and that torque rotate ultimately that fan. And you might remember that the torque produced by the electrical motor is proportional to the square of the system voltage. So if you get 100% of the rated voltage, your fan will rotate at 100% speed. But if you get only 80% of the voltage, rated voltage, then your fan will rotate not at the 80, even at 80%, it will rotate at 64%, because it is the square, the torque produced is proportional to the square of the voltage. Similarly, our bulb, if the light produced by the bulb or heat generation is proportional to the square of the voltage. So most of the load is called the constant impedance load and are sensitive by the voltage square. Their output changes by the square of the voltage they get. So that means it must be of stable. And also the frequency is very sensitive things, that it should not be very high frequency, or again also it should not be very low frequency. There are merit and demerit of all these, because if there are so many devices which are on off, we pulse and other things, but if the frequency becomes very slow, then it may stop where at this. Or if the frequency is very high, then your impedance becomes higher, and in transformer, for example, losses becomes higher. There are so many. So there may be one lecture is required just to why we need the 50 hours or 60 hours, and why not 100 hours and 200 hours. But I'm not talking about that, but the deviation should be minimum. That is the requirement. And of course, to meet all this, you know that why energy electrical engineering is becoming more complex. This is just because of this part. Everything you need to make with optimized performance. Like, say you required the 500 5 megawatt, you might be put 100 megawatt transformer everywhere. But no, once you need only the 5 megawatt, you need to put only 5 megawatt. And if you have to make the 100 megawatt, then you need just 200 megawatt transmission, whether it is a transmission line, or whether it is a generation, or whether it is a transformer. uh, Not only that, even during the within that, you have to design a 100 megawatt transmission line in such a way that it is should be built at as far as possible in the with the least cost. That economical part is always embedded with the electrical system design. So now onwards, we should keep in mind that all our choices of the design component should follow this least possible cost. No, just have a power delivery system. As we have seen discussed just now, that the component of the power delivery system near the source carries bulk amount of power, and as it goes towards the near to the customer, is diverges and dispersed and carry less and less and less power. So as power is moved from generation to customer, it is first moved in bulk quantity at high voltage, and as power is dispersed throughout the service territory, it is gradually moved down to lower and lower voltage. While doing so, this voltage, as you can see, this is very important part. This is the main theme of our design also. This you must consider very importantly. That is, when the power is higher, we use high voltage. When the power is lower, we use low voltage. Why it is? Many people say that if you use the high voltage, then the current flow is will be lesser, right? And but I very important. I will just now justify you that high voltage lines in power system are also the high current lines as well. To understand that why the high voltage lines, uh, um, high power lines are high voltage lines also. Just take a very simple example. Now suppose we have a transmission line. This transmission line has to carry a P amount of power over a distance of L meter, right? No, you know that this is our basic objective. Objective again, I repeat, is that P amount of electrical power has to be delivered to a distance of L meter. Then, as you know that in this line we use conductor, and this conductor, depending upon the size of the conductors and material we use, there is certain loss in this conductor, and that loss is expressed, P loss is expressed as I square into the R. You may say that in this diagram I have neither see the I nor the R, from where it has come. This I comes from this P, and this R is coming from, as I mentioned you, based on the material, its size of the conductor, and this L, this I comes. So this I and this P is correlated. If it is single phase, then P VI cos phi. If it is three phase, it is root 3 VI cos phi. If it is multiple circuit three phase, then this P is related as number of circuits into root 3 VI cos phi. For example, double circuit, three phase line, then this is 2, right? So just take initial example of very simple case, this case, that is a three phase single circuit line. In that, from this I we can get from here, this I is equal to P upon root 3 V cos phi, right? So put over here, we will get P square upon 3, I am squaring this root 3, into V square into cos square phi, right? And this R is, as you know, is rho L by A, where this rho is from the quality of the material called resistivity. This comes from the conductor material. This is the property of material, nothing to do with the distance or something like that. And this L, you have no choice. This L is the power for which this P has to be transported, and this A is the size of the conductor, or cross sectional area, or very simply known as size of conductor. Okay, so usually how much it is more significant if we express this power loss in terms of percentage power loss. Percentage power loss. What does it mean by percentage power losses? Percentage power loss is P upon P loss upon how much is the power it is, because 10 megawatt loss in, if we carry the 100 megawatt and 1000 megawatt is not the same, but saying 10% or 1% is more meaningful. So that's why I'm converting this power loss expression in as a percentage power loss. So you can see that if we do this percentage power loss, then it becomes P square. P square now gets cancelled because you are divided by P. Exactly the same equation, only difference will be this P square will be changed to P. So this equation becomes P rho L by 3 V square cos square phi into A. Right? Now, in this equation, try to make those parts which varies but very little and which can vary over a wide range. Just explore those things. How much you expect the variation in, say, variation in V? Variation in V, maximum worst condition could be in per unit, say 1 to 0.8. Okay. So keep it that, okay, this voltage, now we are in design phase, so we have the choice of the voltage, so this voltage can also vary, okay, over wide range. Now the variation in, say, for example, cos phi power factor, it can vary maximum 1 to 0.8, right? This row I will discuss in one of the separate chapter, that why we use the aluminum conductor or ACSR very frequently. So in transmission line, often we use the aluminum conductor. So that means this row is also very much constant. Then if variation in this cos phi and rho, why we are saying that this cos phi variation is less is with respect to L. This L could vary from 1 to thousands of meter, or say in some cases we may just have to transport the power of 1 kilometer, in another cases we may require to transport the power for 1000 kilometers. So variation is wide range. P similar for the P, this P you have to carry sometimes 1 megawatt and sometimes thousands of megawatt. So if we rearrange this equation, I can write this as PL by V square into A. These are the more variable part, but the less variable or constant part is this. Even in case of, you know that even in transmission line, the power factor will not allow low as say this zero point 0.8, because the power factor, if the power factor is lower, the system losses will be higher. And since reactive power we can also generate locally, so this power factor, of course, is lower in the distribution system. But as we move for the higher or power system part line or transmission line section, or where the bulk amount of power is transmitted, we try to keep the power factor as more as possible. That you might have studied, and we again discuss this in later part of this course also. So what I am telling you is the variation or of the variation of in this section is less with respect to this. And here one alarming part in this equation, as you can see, is that the percentage power loss itself is proportional to P. What does it mean? If you keep, if rest of the everything same, if you keep the rest of everything is the same, then if you, the power loss for 100 megawatt, percentage power loss for 100 megawatt will be 10 times greater than what would have been the case for 10 megawatt, right? So that means the percentage power loss itself is proportional to P, proportional to the distance over which it has to be transmitted, and inversely proportional to the voltage square, and also inversely proportional to the cross sectional area. Usually what is our desire is this percentage power loss should be as low as possible if we transmit more and more power. But here the situation is reverse. If we keep rest of the everything same, we can see that if the power transmitted is more and more, the percentage power loss is higher and higher. So just for a moment, what we do is assume that our desire is percentage power loss we want to keep as constant. So if we want a fixed percentage of power loss for a fixed, for a for a fixed percentage power loss, What remains that this PL by V square A into some constant, because I have told you that this part variation is very less, is equal to some another constant. Or we can say that, no, suppose you may say that, okay, uh, we can vary this loss. Instead of variation of the voltage, I vary this loss by varying the conductor size. So what would have been the conductor size if, now, see, you don't have the choice over P and L. This P and L has to be, P amount of power has to be transmitted over L. So in this equation, you have the choice only for in the during the design case, you have the choice for V. You can choose the different voltage. You can choose the different size of the conductor. So in one first case, suppose that we do not varying the voltage, but we are varying the only the conductor side. So here A from this equation can be set some constant into PL by V square, right? What does this the cross sectional area of the conductor indicate? It is this cross sectional area of the conductor is also indicative of the volume of the conductor per unit length, right? Or volume of the per unit length of the conductor is also indicative of the cost of the conductor per unit length, right? So what I mean is, this part is the indicative of cost of conductor per unit length, not the cost of the conductor per of total length. It's the cost, because this is the cross sectional area. So cross sectional area signifies only per unit length. If you multiply this with the L, then it becomes the volume of the conductor throughout the length. So I have not multiplied this cross sectional area with L. So this part is the indicative of the cost of conductor per unit length. And as it can be seen that the cost of conductor is in for or just summarize this equation, for a given amount of power to be transmitted over a given distance, the cost, of course, per unit length of conductor is inversely proportional to the square of the voltage, right? Yes, just we have discussed here one thing. Okay, right? uh okay, why the NC I have previously, I will come back again how the NC has coming here, but right now just ignore that. Then we have already discuss that how these equations are coming. And as you have seen that this is the nature will come look like this, inversely proportional to a square of the voltage. So as we go on increasing the voltage, the cost of conductor per unit length is proportional to, of course, this curve. If this is the V, and as you can see that this curve has been plotted just as an 1 by V square, something proportional to V square. So cost of conductor is proportional to a square of the voltage. So higher the voltage we choose, lower will be the cost of the conductor. then the natural question arises that if this is true, then why not we use always the high voltage? Whether we have to transmit the 10 megawatt or 1000 megawatt, we use the higher voltage, because choosing the higher voltage always reduces the cost of the conductor. हेलो, तपाईहरुको क्लास चाहिँ छ यसपछि? हेलो,
छ सर।
अहिले क्लास छ अर्को?
छ सर।
त्यसो भए त स्टप गर्नुपर्ने होला है?
हजुर सर, हाम्रो 55 देखि नै हो अब अर्को कुरा।
कति?
55
एक मिनट बाँकी छ।
मिनेट पछि।
ए त्यही त भनेको 55 हुन लाग्यो, त्यही भएर मैले सोधेको। ठिकै छ, त्यसो भए आज यही स्टप गरौँ है।